Cool, so hi DEF CON. I'm Redezem. Don't ask about the name, it involves an incident with a Caesar cipher at a preschool. Welcome to PEIMA DEF CON edition, where we're going to talk about how to break denial of service attacks and do anomaly detection on the cheap. This is mostly a defense talk, so no cool exploits, sorry. But there is a lot we can play around with here, and so if you like hacking, this is probably for you. Alright, so who am I? My real name is Stefan. I am, by most accounts, a PhD student. I live in the beach and sunshiny wastes of Perth, Western Australia, which is about 28 hours worth of flying time from here. The bonus is that the weather's basically the same over there in summer, so I mean the heat's been kind of meh. Now I'm a network kind of guy. I love my networks and network security. I work in research with Curtin University. That's the first logo, in case you were confused. I also work with a company called ES2, which lets me do my hacking stuff. They're the second logo. They're some great guys. If you're in the Perth region, call them up. They're lots of fun to hang with. Cool. So what are we talking about today? We're talking about how you can use power laws to protect your stuff, basically. In short, this is anomaly detection without any sort of AI whatsoever. It's pretty great. So we're going to have a look at what they are, how they work, what I've been using them for, which is denial of service defense. And we're going to look at what the research shows is possible and consequentially where your hacking sort of efforts would be really, really useful and probably get you some serious cred. And then I'll release a neat tool to get you on your way and a demo that can show you what you can actually do with it if you work with it. So, power laws, or more honestly, power law probability distributions, which is a mouthful, so nobody's got time for that. Basically, there are natural processes out there in nature. Earthquakes, light from stars, mutation in DNA, language, that sort of thing. The things that are descriptive of these things tend to follow these things called power law distributions, which is the second graph over there. There are a couple of popular ones that are well known. Relatively speaking, Vsauce did a great video on Zipf's law that you should totally watch if you're interested in this sort of thing. But yeah, so Zipf's law basically says if you've got, because language is a natural process, if you take a book and count all of the words in the book, the second most popular word will appear about half as much as the first most, and the third most popular word appears about a third much as the first most, and so on and so forth. And it's really weird because it works in every single language, in every single book, period. Which is bizarre. We have no idea why. This also works for financial transactions. You can use this to detect fraud because, funnily enough, when something should be following a power law and isn't, something's wrong. And it's very, very sensitive to that. So banks have been using this for ages, and we've only started using this in network security in the last year. So what does that mean for us? Well, basically, network traffic is somehow natural, which means that Skynet is real, the singularity is here, Elon Musk was right, and we're all going to die. Seriously though, it just means we can apply power laws to it to do anomaly detection without any sort of AI to it, because what we do know is that under normal circumstances it should follow one of these power laws. Things should follow power laws in network detection, and if they don't, we already know that something is wrong. Cool. The neat bit about this for denial of service attacks is that thanks to the nature of denial of service attacks wanting to, specifically flood-based denial of service attacks wanting to overwhelm a network, you can't actually do one without breaking a power law. So I will know you're doing it. Cool, so basically we don't have to teach a computer what normal is anymore, so no AI, great stuff. The cool one is Benford's law, which you can hard code because it never changes. Basically, if you have a number that's long enough, say the amount of time in milliseconds between any two packets arriving on a system, we know that the probability that the first digit is 1 is about 30%. We actually know what the probability for all digits in that number, being any given number, is, which is great, and conveniently the whole thing never changes, so you can just hard code it and away you go. What can we do with that? Well, I've been beating denial of service with it for the last 6 months. Basically flood-based denial of service attacks. Amplification attacks are particularly good. The sort of things that the Internet of Things is likely to cause more of, as more of these ridiculously insecure devices enter the Internet. So basically in this graph here you can see 10 separate denial of service attacks, one after the other. It's actually on a network where we've got a bunch of gamers playing Unreal Tournament 99 and someone's trying to stop them from winning. Because, we like blasts from the past and whatnot. So the higher that number, so the higher that line goes, the worse its error from Benford's law is, and you can easily see when your denial of service happens. This is a single machine. You throw more machines in there, you make it a larger attack, it becomes more ridiculous. It's practically instantaneous too. Each data point in that graph represents about 1,000 packets, a window about 1,000 packets in length, which takes about, a couple of milliseconds to appear. So we know about the attack starting and stopping within milliseconds of it happening. And I've seen it work in real time in gigabit scenarios, and it's likely it's capable of actually going even faster, so you can do some really cool stuff with this. Again, it detects this without any training whatsoever. I didn't have to train anything, I just said, when the number is greater than 0.5, tell me a denial of service attack is happening, and it's pretty much always accurate. So how do we do it? Well, it's really, really cheap. We get ourselves a TCP dump. It's a really complex piece of software. We get it to dump in -NN, so just we want to get the headers and none of that cool, resolving thing. We extract features, namely the length and what their timestamp is. We check how well those features fit power laws via a goodness of fit function. If you want to investigate more of these, please look at the code and the demo I'm going to be in the tool I'm going to be releasing. You print out the result to a CSV and throw an alarm or something. And this works with any subset of traffic data, so you can actually narrow this down by excluding the people you know are good until eventually you figure out exactly who the people that are, denial of servicing you, and you can probably change your IP tables at that point to drop their packets. So what can you do? Well, unless you're a really big company, this probably won't save your network, because if someone wants to distribute a denial of service attack you, we saw with Krebs 600 gigabits a second, I'm not entirely sure your router can deal with that. But what you can do is you can look for attacks and you can tell where they're coming from. So you can report to your ISP and say, hey, I'm being denial of service by these people, and that makes their life a lot easier. You can actually invert this too and look at your own network. So you can turn around and say, hey, my laptop is sending out a denial of service attack. Who the heck has owned my laptop? Which is great, because that means you're probably part of a botnet and you want to go and flash that thing. Right, so what else can you do? Well, research. We can see that you can actually see more than just a denial of service, because obviously that's not the only disturbance on a network. You can see some attacks. Now, the attacks we have seen so far are Nmap and some buffer overflow style attacks, specifically for NGINX. You can see them happening, but that's because I'm not doing anything smart with my detection. I'm literally drawing a line and saying, if it's above that, there's something wrong. You can actually probably train something to figure out the shapes of each of these attacks, because each spike looks slightly different. That one there is an Nmap port scan, so not using the Nmap scripting engine. So yeah, you could tell that trained thing to make decisions for you, and yeah, it's pretty cool. We don't know exactly what the limit of the threats are that you can detect, and pretty much anything that happens will change how your network works, and power laws are really good at picking up that. So some disturbances aren't attacks. Power laws are really great at telling when that underlying process that's creating your traffic changes. In this graph here, there's actually some kind of anomaly. Sure, there's some spikes there, but the one we're actually looking at here is the big bump in the middle of it. That's actually when everyone starts logging in at 6 a.m. in the morning. We can actually tell when people start logging in just by looking at the Benford's law compliance of the data. It's pretty cool. So basically, if you see a change that isn't regular and doesn't match with any of your activities, you might see someone doing something to your network, doing something to one of your computers, or something is broken. And that's pretty helpful too, I guess. However, that's not the only things we can look for changes in. We can look for changes in your user. You see, humans are pretty natural, right? Language is natural, finances are natural, they're both done by humans. Well, turns out users interacting with keyboards is also pretty natural in terms of process. We've actually seen in research that you can turn around and take the time between each key press you make. And that actually conforms with Zipf's law, the law that actually, language conforms with. So whenever you actually change user, the error slightly changes. If you, instead of looking at how well it conforms with Benford's law, you look at the difference between the actual law itself and what you do, so what the errors are individually, and you save that as a profile, whenever you're using the computer, you'll be around about that profile. And whenever someone else uses your computer, they'll be completely different. And you can immediately tell that someone is using a computer and you didn't ask them to. So keyboards are great and all, but that's not the only thing you can do. Because it's entirely based on human interaction, you can probably extend this to all sorts of stuff. Command usage, network usage for that user, etc., etc. So when your computer determines that something is up here, you can turn around and tell it to start doing stuff. You can say, oh, I'd better start a keylogger. Or start sandboxing things, denying access to things, whatever. Be creative. Speaking of being creative, we have no idea where this goes. This has been looked into for the last 6 months by research teams who are notoriously slow. So hacking input is great. That's what I've been doing with the denial of service thing, and that's pretty much the furthest we've got. So the tool I'm handing out today is basically here's basically where I'm up to. This is how you can do some power law analysis. Start putting stuff in and see what you get. It's everywhere. There's a lot of stuff this can be applied to. We don't even know the limits of the network detection capacity. And we think we can apply it to pretty much anything that has to do with a computer. So this might be really, really cool if you're an engineer wanting to play around with something. And it's basically really fast and simple to play around with anyway, so why not? So, now, the tool. So, bear with me here. Whoa. Whoa. No! Come back, screen. Hey, AV guys. I can't do a demo when the screen's blank. Can you help, please? Please? Well, while that's happening, I'll set this up so we just jump straight into it, right? I think that's fair enough. No. Yeah, sure.
If I'm looking at data that isn't really natural, is this still maybe an interesting metric to look at?
Oh yeah, sure, no, because the human data, right, with keyboard stuff. Question being, is this a good thing to look at with stuff that isn't natural? Human keyboard data, they figured out you can actually do profiling just based on the Benford's law, which doesn't conform with keyboards at all, right? So it's completely erroneous, but the profile of error from the user was actually able to be used as a profile just as well as the Zipf's law stuff. So even if something isn't natural, yeah, there are things you can do with this. It's really, really good at telling when something has been changed. So. Oh, really? Well, that's odd. It's plugged in. Okay, I'll unplug and we'll plug it back in. No, same operating system. Yep. Taken out themselves? They probably. Sorry. Is there a history of banks being taken offline for 4 or 5 hours by denial of service attacks? Maybe. I'm not exactly sure. I'm pretty sure that's happened before. Oh, well, there you go. Like the important thing here is that, distributed denial of service attacks, specifically ones that you'd expect from, your Internet of Things devices, are going to get like significantly more common over the next 10 to 20 years. Sorry, just reset. Yep.
So what's the overhead on running this calculation? Obviously you said you can handle a lot of data really fast, but if you wanted to say, look at particular IP addresses inside the network to determine who's actually sending the denial of service out,
yep.
Like what's the O of N?
Okay, so what's the O of N on the actual detections? I'm pretty sure it's ON squared. So it's not slow, like super slow, but it's not ultra fast. I mean, that's mostly due to my tool being pretty damn slow. You can probably make this a lot faster. I mean, I've written the tool in basically Python, so.
Perfect.
Python 2 rules, screw Python 3. Yes. Showing drops in traffic. Ooh. Different. Yeah. No, it wasn't on the presentation.
Can you pull your presentation back up?
Oh, sure. Okay, so if I put this back up. What? Okay, so we can do the presentation bit, but we can't do the... Okay, cool. All right, let's see. Duplicate.
There you go.
Oh, thank God for that. Thank you, guys. The AV team, everyone. All right. So, the demo, right? It's sitting on Bitbucket because I'm a terrible person and I like Mercurial. Cool. The address is on the slides. Take a shot when I switch back to the slides. But basically, here we've got your typical, nmap output. You cat that into the preprocessor. It'll strip out timestamps, IP addresses, ports from and to, and a bunch of lengths and the IP flags. So if you're interested in that sort of thing, obviously these aren't all used for my for the analysis and the tool itself, but they basically give you some really, really quick extensibility options. And if you then pipe that to the power law processor and give it, say, Benford's for inter-arrival time, with a nice little CSV of all of the goodness of fit values in their timestamps, which, if you then run against... so we've got one that I prepared earlier because, that's nice of me. Yep. If you then go Python, plot, code, plot, output, if we pop over to here, hey presto, you can see when a denial of service attack is happening. Of course, that's me being human and looking, but again, if you drew a line above 0.05, you'd be going, hey, something's gone wrong as a program. Take a shot of... Oh, shit. That's not what I wanted. Damn you, Microsoft. All right, cool. So there you go. Right there. Grab a shot of that. Whoa. Oh, no, it just crashed. All right. Did everyone get that? Okay. Let's try that again. Please, Microsoft. Hey, I'm not gonna click it. Just take a shot, right? My email will be at the end slide. Take a shot of that too. Okay, so last thing to do. Magic trick. We're going to do some Unreal Tournament denial of service direct inline mitigation without knowing anything about the attacker. We cool doing that or? Okay, cool. 1 minute. Cool. So we got the server with a user and a server. We've got a user. We got Kali. I will jump to the fun part of this because I do not have much time. Thank you. AV screwy things. Right, cool. So here we've got the guy up top here. This is the server. We've got... Oh, shit. It's gone and done that thing where it's... stop extending. All right. Cool. There we go. Can we see it now? All right. This guy is the server. This guy is the player. This guy is our really nice secret project filter in the middle in the gateway. And this is Kali. If I jump ahead... here... we can see I'm doing hping to launch an attack, right? The filter detects it. Wait for it. Right, so the filter's detected it, and it's currently actively mitigating the attack. It is looking at individual packets and determining whether or not they are denial of service packets. It is not determining whether or not the machine that is attacking it is actually a bad guy. As you can see, there's no lag. If I jump a bit forward, I've actually turned it off. Here we go. And as you can see, the player can no longer play. There's a big jump in traffic on the server. If we jump over to here, yeah, you can see up the top there that we are now seriously lagging because, again, it actually is a denial of service attack on. So that's without the filter. And if we jump forward again, when we switch it back on, there you go. So you can see that the traffic has dropped again. The thing can detect an attack. It is currently mitigating. And yeah, there's no lag. So we've successfully used this to directly inline mitigate a denial of service attack. So that is it. Thank you very much.